So now we're going to consider the small sample case here. That is when your sample sizes N1 and N2 are less than 30. So the test requirements in this case are that you need independent random samples from two populations. That's the same. But then both populations must be approximately normal here. So that's because we've got small sample size. So remember, if sample size is big enough, you don't need approximately normal populations because the sampling distribution will still be normal. If you've got these small sample sizes, you need approximately normal populations. And then the variance or the standard deviation for the two populations needs to be the same. We call it common variance sigma squared. So in the case of small samples, we use what's called a pooled estimator here for the variance. So it's called S sub p squared, and it's the sum of xi minus x1 bar squared plus the sum of xi minus x2 bar squared for the appropriate samples, and then you divide by the total of the two sample sizes minus 2. That's considered your degrees of freedom in this case. And you can show by algebraic manipulation that this is the same as n1 minus 1 times s1 squared plus n2 minus 1 times s2 squared over that same LCD. So this expression here is actually a weighted average of s1 squared and s2 squared. Remembering here that sigma squared is the sum of xi minus x bar squared and then divide by n. And if this is s, this will be n minus 1 in the denominator. So notice that's similar structure here. Except we've got n1 plus n2 in the denominator, but then if we split these over the LCD, we have a weighted average here. So it's a weighted average where we're weighted by the sample sizes. So the bigger sample size here, we're going to include a higher weight of its standard deviation, sample standard deviation. And then our small sample confidence interval looks like the difference of the two sample means plus or minus t alpha over 2. So we're using t distribution with small samples, just like we did with the one sample test. And then this expression here, that is our standard error or standard deviation of the sampling distribution for x1 bar minus x2 bar. So we've got the same setup of point estimate plus or minus a t-value times standard deviation. And again, sp squared right here. So your pooled estimate. So when you do that in the calculator, you can do this in the TI. You do stat test 2 sample t interval. And then you'll input your summary statistics or your data, select whether it's directional or non-directional test, select yes for pooled estimator, and then calculate. So that's quite a bit different than for one small sample. Small sample test of hypothesis for the difference in means. For a one-tailed test, your H0 is going to be mean 1 minus mean 2 equals D0 is a hypothesized difference. This is usually 0. And your alternative would be mean 1 minus mean 2 less than 0 or greater than 0. For two-tailed tests, it's equal and not equal. And so this null hypothesis most of the time is saying mean 1 equals mean 2, and this alternative would be mean 1 less than mean 2. This would be mean 1 not equal to mean 2. So then our test statistic here, again, this is usually 0, will be the difference of the two sample means. And then again, we're dividing by that standard deviation of the sampling distribution. So again, this is our sigma of x1 bar minus x2 bar. So that has the same general setup here as you did with one sample. And then your rejection regions are going to be t greater than t alpha or t less than minus t alpha for one-tailed, and then for two-tailed less than minus T alpha over 2 or greater than positive T alpha over 2.